Bismillahirrahmanirrahim. ELE424 Analog Electronics 1 Bipolar Junction Transistor DC Biasing. We have completed in our previous video lecture BJT of the device itself. We are now ready for the next topic, which is DC biasing circuit, focusing on fixed bias for this slide. I am Wan Fazlida Hanim Abdullah. I'm from Faculty of Electrical Engineering, University Technology Mara, UiTM, Malaysia. Topics covered in BJT DC biasing, fixed bias for this slide is first we're going to have a look at the introduction. Again, my introduction is aims to give my students the appreciation of why it is required in the first place. So why DC biasing is required, why there is a need for different kinds of DC biasing circuits, and what we would want to find out about from the DC biasing circuits, or for the design of the DC biasing circuits. And then we're going to have a look at for the simplest DC biasing circuit, which is a fixed bias circuit configuration. We're going to have a look at the circuit, the analysis of the input loop, analysis of the output loop, load line, and transistor in saturation. After this configuration, there'll be other DC biasing circuits that we will look at, which is the emitter stabilized bias, voltage divider bias, collector feedback, emitter follower, and common base. Now, we're not going to have enough time to cover all possible DC biasing circuits, but this is what is covered in the syllabus. So for the introduction, why is DC biasing required? From previous lecture, we did mention that as was stated in the introduction of BJT device, an amplifier system is able to amplify an AC input signal. Meaning, if you have an amplifier system, you give it a small signal of AC input signal, this amplifier system can amplify the either voltage or current or the power of the signal that is being that has been fed to the amplifier system. And the amplification device, that is the key device in the amplifier system, is the transistor. So if we have a BJT in the amplifier system, so this amplifier system here can receive an input and produce an output, just as is illustrated in the diagram above. And this BJT will have to be biased by a DC biasing circuit before it can amplify input to output. So BJT in linear amplification operates in active region. Okay, I'm again repeating myself as was mentioned in the previous lecture. So emitter base junction needs to be forward biased and collector base junction needs to be reverse biased. But the biasing to the emitter base and collector base junction is provided by this DC biasing circuit before it can actually amplify. Another way of looking at it is that the biasing circuit is required to ensure that the BJT operates at the intended Q point in the output characteristics. Last video lecture we covered this output characteristics, and we mentioned something about Q point, and we said that the BJT has to operate at the intended Q point. So this DC biasing circuit is the part that is the part of the design that is responsible in ensuring that the BJT operation is at the intended Q point. So amplification also involves increase in electrical energy, as we can see in the simple diagram here. So the external energy required for signal amplification comes from the DC power supply in the biasing circuit. Okay, that's also another way of stating the requirement of the DC biasing circuit. Okay, so why is DC biasing circuit required? So last lecture we mentioned that the biasing of emitter base and collector base was shown using voltage sources such as in the picture here. Okay, so but there was no connection showing terminals to input nor output. Okay, this is an emitter base junction, and this is to show the concept. So this connection was just demonstrating the concept, but not an actual application of biasing the circuit. So in a real electronic circuit connection, there is only one DC voltage source. Okay, we don't have separate voltage sources for VEE and VCC. We have one DC voltage source, and the biasing needs to be achieved using resistor networks. So for us to achieve the forward bias of the base emitter junction and the reverse bias of the collector base emitter junction is through this resistive network that is connected to the BJT. So here we show the simplest DC biasing circuit, which is the fixed bias configuration that we will focus on this video lecture. So in this DC biasing circuit, BJT is in the common emitter configuration because the emitter terminal is the closest to ground, where one of the terminals have to receive the input signal, which is the base, and the other two to be in the flow of the output signal, which is the collector and emitter. So from here we have an input characteristics, which is IB versus VBE, and the output characteristics, which is IC versus VCE. Still at the introduction, just so that we see where we're going, we will cover 6 circuit topologies: fixed bias circuit, emitter stabilized bias, voltage divider bias, which is through exact analysis and approximate analysis, collector feedback, emitter follower, and the common base configuration. So why are there variations of DC biasing circuits? So BJTs are known to be sensitive to temperature, causing the current behavior to be different than what it has been designed for. So to improve sensitivity and stability, some modifications are done onto the fixed bias DC biasing circuit, which is the most basic. Okay, these improvements, these modifications would improve the sensitivity and the stability of the Q point. Okay, so these are some examples. We will start with the fixed bias, and then we can have the emitter stabilized bias, the collector feedback, and the voltage divider bias. So we will see how all this DC biasing circuit operate, and the different circuits. There are also different circuits needs that may also require the BJT to be connected in different configurations, such as driving load with higher current instead of amplifying the emitter input signal like the emitter follower, and the needs are many, and so are the design variations. So what we can cover here are just a few configurations for examples. Yeah. So what do we need to find out about the DC biasing? Okay, so first we need to find out what resistor values would set the operating point, the region that is required for the behavior of the specific BJT for the given architecture. Okay. Second, the resistor values must also ensure that the BJT operates within allowable power ratings, not just to ensure that it is in the active region, but also within allowable power ratings. And all DC biasing circuits will have input network as well as output network. So the output characteristics will have the suitable parameters based on the configuration of the DC biasing circuit. And be prepared that we will be using again Kirchhoff voltage law, which is simple circuit analysis tools, knowledge of parallel resistance, Thevenin equivalent circuits for some of the configurations, and the ability to redraw simple resistive network connections. So this is just preparing you mentally on what to expect in the next few slides. Fixed bias configuration. Okay, we are done with the introduction. Now let's have a look at the fixed bias configuration. This is the fixed bias configuration. This is the circuit. Okay, we have the BJT. It is connected in a common emitter configuration. There is an RB resistor that is connected from VCC to the base. There is RC, which is connected from VCC to collector. AC input signal is received at the base terminal, and the output signal is taken from the collector terminal. And this is the simplest DC bias configuration. The BJT in the DC bias circuit is biased as required by the circuit so that when it receives an AC input signal, it can amplify it to an AC output signal. Again, I'm just restating again and again the purpose of the DC biasing circuit. Okay. To perform DC analysis, okay, we know that the actual application of the circuit is going to be amplifying the AC input signal to the output signal, but before we can do that analysis, we need to do the DC analysis first. So to perform the DC analysis, we need to redraw the circuit and set it for DC only. And how do we do that? Redrawing for DC analysis. Okay. The capacitance, the coupling capacitance at the input and output. To perform DC analysis, the network can be isolated from the indicated AC levels by replacing the capacitors with an open circuit. Again, how is that possible? It's because when we're doing DC, okay, if we look at the reactance of capacitance, it is a function of the applied frequency. So for DC, the frequency is 0 Hz, and therefore the reactance acts like an open circuit. And when we do DC analysis, we will separate the input section, which is VCC, RB, and the base terminal, from the output section, which is VCC, RC, collector, and emitter. So sometimes we draw the supply separately to allow easier visualization when redrawing for KVL. It's the same actually. Okay, in the previous circuit, we drew it just connected to the same VCC, but here we separated. So I'm just pointing this out. This is not significant, but I'm just pointing it out just in case you get confused. It's not that we have two separate voltage sources, it's actually the same, and it is common. Take note that circuits with nodes of the same name and the same schematics are connected directly together. Before we proceed, let's have a quick revision of voltage at a node versus voltage across an element. I can't emphasize this more important enough. Okay, when the slides turn yellow like this, it means that we're actually going for a flashback. We're doing a quick revision. Okay, this is not actually in the lecture notes flow. Okay, but I feel that we need to sort this out very clearly. Now, let's say we have a connection of resistive network here of R1 and R2. R1 is connected between node A and node B, and R2 is connected between node B and node C. Now when we want to measure the voltages across R1 and R2, we have to be very clear whether we want to measure the voltage at node A or voltage across R1, because voltage at node A refers to the voltage from the node to the ground. So if I have this connection, it's between node A and ground, and it will give the value of voltage at node A. But if I have voltage, if I want voltage across an element, which is the voltage across R1, that it would refer to the voltage from node A to node B, like this. Okay, so the black terminal of the multimeter would go to node B. And if I were to see, let's say this connection here, let's say VA, is this just an assumption, just example, let's say VA is 10 volts, and let's say voltage at node B is 8 volts. But if I had the previous connection of voltage between node A and node B, which is the voltage across the element of R1, okay, VAB, it would be 10 minus 8, which would give me 2 volts. And if I were to say, let's say for example, the voltage between, let's say VC is 5 volts, and if I were to measure between B and C, which is the voltage across R2, it would be 8 minus 5, which would give me 3 volts. And if I were to measure, let's say, the voltage between A and C, because voltage A is 10 volts and voltage C is 5 volts, the voltage across these two nodes from A to C would be 10 minus 5, which is equals to 5 volts. Okay, so we have to understand what the difference is. The reason why I've pointed it out is because sometimes we have voltage that we are measuring is sometimes at the node, at the collector node, which is VC, and that refers to the measurement from the voltage at collector between the collector and the ground. But if we are saying VCE, then it would be between the collector and emitter. But sometimes if the emitter is at the ground, VC is equals to VCE. But sometimes if I have a resistor here connected between the emitter terminal and the ground, then VCE will not be the same as VC. Okay, we will now leave the revision slide and go back to the main topic. So we said that this was the fixed bias configuration. Now what I'm going to do is that we're going to analyze the input loop first, and then we're going to analyze the output loop. Now this analysis will be required when you're actually analyzing a circuit that is given to you. Okay, so let's have a look at the input loop first. So analyzing the input loop, Okay, we know that the input loop, now the purpose of the input loop is to ensure that the emitter-based junction is forward biased. When the emitter junction is forward biased, then VBE is going to be set at a value of around 0.7 volts. It's just a rule of thumb, okay? It's not it doesn't have to be the same for every case. It's going to be maybe something slightly bigger or something slightly smaller, but that is just a good rule of thumb. Okay, so if I were to analyze it, I take that circuit and do just on the input loop, and I can do a Kirchhoff voltage law. That just let me go to the previous illustration. Okay, so I have here RB, VCC, RB, and VBE. So this would be the input loop. I'm going to draw this loop here. Okay, so RB, VBE, and the VCC. Okay, and if I do a Kirchhoff voltage law around this loop, I'm going to get minus VCC plus VRB, which is by Ohm's law would give me IBRB, plus VBE equals to 0. Okay, and if I were to rearrange this, IB is going to be equals to VCC minus VBE divided by RB. So VCC is usually decided for the circuit, okay, in the beginning of the design, and you don't change it across the design because the whole circuit would require the same VCC. VBE depends on the material of the BJT device itself, which I said earlier, which is going to be around 0.7 volts. And RB here is your design parameter here, which means what you're saying here is that, so some observations, RB is the value that sets IB. Okay, so now first let's have a look at the slides here. VRB, which is here, okay, is the remaining of the voltage drop from VCC having forward bias the emitter base junction VBE. Okay, so this is what this point here is saying, because you have VCC that goes from the power supply to the ground. The total voltage drop here is going to be equals to VRB plus VBE. So VBE is about 0.7, and the rest of it will be the voltage drop across RB. And that RB here sets the level of IB for the operating point. Okay, RB sets the level of IB for the operating point that is intended. Now let's go to the output loop. We know that the transistor characteristics from the previous slide, it says that IC is equals to beta IB. Okay, so IC is going to be equal to beta IB. IB is set by RB, and then IC is equals to beta IB. Where is this beta coming from? This value of beta is the behavior of this transistor. Okay, now let's analyze the output loop, and the output consists of IC and VCE. So we will analyze the output loop to get expressions of output IC and VCE. I'm going to redraw this. Okay, I'm going to redraw this with VCC, RC, and VCE like this. Okay, RC, this is RC, and VCE and VCC. And again, I can do an output loop KVL, and I'll get positive VC minus VCE minus VRC equals to 0. And again, this is Ohm's law. VRC will give me ICRC. Rearranging, I can get this expression. VCE is equals to VCC minus ICRC. So some observations. IC is set by IB and not the characteristics of BJT. It's not by RC. IC is set by beta times IB. Beta is the behavior of this transistor. IB was set by RB. So IC is not set by RC. RC sets VCE instead. RC sets VCE for the operating point. And we know that VCE must be greater than VCE set because we said that the collector base junction must be reverse biased. So we don't actually design from keeping tab of VCB, V collector bias, but instead for an actual implementation of the DC biasing circuit, we set VCE by setting RC. So VCE must be greater than VCE set, okay, to ensure active region operation, but less than VCE max. If I can just bring you back to the input-output characteristics, okay, we have here a value of, this is a bit too small because there's too many things that I want to put in this slide, but here is, we have VCE set, okay, because at this point, if you make it any smaller, the collector base junction would be going into forward bias, and if you have both junctions forward bias, BJT would be operating in saturation. So it has, whatever RC is, it cannot cause VCE to be smaller than VCE set, but to ensure that safe performance within the power ratings, it has to also be less than VCE max. Okay, you might want to have a look at the slides indicating the maximum power ratings in the previous video lecture. Okay, let's do an example. Now we're ready for an example. Determine the following for the fixed bias configuration. You have a fixed bias configuration, you have an actual resistor value here of 240k for RB and 2.2 kilo ohm for RC. Okay, and beta is given to be 50. Let's find out what the operating point IBQ and ICQ is. This value of IB and IC, which is determined by this DC biasing circuit in its operating point, Q point. Okay, that's why there is a Q here. And let's find out what VCE is for VCEQ, and find out what VB is, the voltage at the node base terminal, and the voltage at the collector terminal. And let's find out what VBC is, because we said we wanted the emitter base to be forward biased and the collector base to be reverse biased. But again, we don't design by looking at VBC, we design by looking at VCE. And VBE is the power PN junction forward bias at 0.7 volts that is given. Okay, this is how my solution looks like on paper. Okay, but this is too small, so what I'm going to do is that I'm going to show section by section in the previous slides, in the next slides. Okay, redrawing for DC analysis. So I have here, I'm going to redraw this because these have elements of capacitance. So like I said just now, we can remove this AC coupling capacitance value with an open circuit. Okay, and I have separated the 12 volts power supply for the input loop and the output loop. Okay, just so that it makes it easier for me to visualize it. So having drawn for the DC analysis, I shall next do the input loop. So from the input loop, okay, I do an Ohm's law and I get this expression for IB, okay, and I get IB's value to be 47.08 microamp. And from the transistor characteristics, which has given as beta, which is equals to 50, I find IC to be equals to 50 times 47.08 microamps to be at 2.35 milliamps. And then I do next for the output loop. Okay, so for the output loop, again I do a simple redrawing of the circuit, and then we do a simple KVL to get the value of VCE. So minus VCC minus VCE plus minus VRC is equals to 0. So I get the value of VCE to be 6.83 volts, and the operating point for VCE is 6.83 volts. So now we have established the operating point. IBQ to be 47 microamps, ICQ to be 2.35 milliamps, and VCEQ to be 6.83 volts. Now before I go and answer question part C, I'd just like to point out that there are a lot of DC biasing circuits in your course of studying ELE424. Don't memorize these expressions for all the possible DC biasing, because it's not that difficult to redraw the input loop and just do a simple KVL and Ohm's law. Okay, you get the expression. And redraw the output loop to get again the expression here. Okay, so I'm in my examples, you will see that I just redraw here. These are not theorems. Okay, these expressions here, minus VCC plus IB, RB plus VBE, and this expression here, VCC minus VCE minus VRC equals to 0. These are not theorems. These are dependent on the circuit that you have to handle. So do the analysis as required, because it's not that difficult. Okay. Right, and then here, part C wants us to find what the node at the voltage note what the voltage at the base terminal is, and the voltage at the collector terminal is. So VBE is VB minus VE. Okay, so VB is 0.7 volts, and VCE is the voltage across terminals VC minus VE, so you get VC to be 6.83 volts. Okay, why are we doing this? Because we want to find out what VBC is, and VBC is going to be 0.7 minus 6.83, which gives us a negative 6.13 volts. So B is P-type and C is N-type. So here the voltage from the P to N is a negative voltage, so the base collector junction is reverse biased. So the emitter base junction, okay, we have stated it, taken it to be at 0.7 to be forward biased, and we have shown that RC, that value of RC that has been given to us, keeps the base collector junction to be in its reverse biased, so that's good. Okay, now leaving the example, let's have a look at the output loop more, and I'm going to introduce here the concept of load line. From the expression of KVL of the output loop, okay, a linear expression y equals to mx plus c can be written with the axis y being IC and x being VCE. Okay, this was the output loop. We did a KVL, remember? So we had this expression. Now we can, this is actually a linear expression, and we know that the output characteristics is IC versus VCE. So IC versus VCE, meaning we can write this expression, okay, to represent different values of VCE and IC for values of VCC and RC in a straight line. So this is a linear expression that has information of axis intercepts and slope as shown here, okay, written in the form of y equals to mx plus c, y equals to mx plus c. So the y-intercept is VCC over RC. The x-intercept is when y is equals to 0, and that would give us VCC, and the gradient would be negative 1 over RC. So this line is called a load line. This line here, we can actually draw it as a straight line, and it's called a load line, and it can be drawn superimposed onto the output characteristic axis, which is IC versus VCE, as shown in this slide, like this. So what this plot shows here is the transistor output characteristics IC versus VCE with the superimposed load line, black line, the black straight line here, showing that there is an intercept between the load line and the transistor output characteristics of the quiescent point, Q point of IB that has been fixed. And so this intercept here will give you ICQ and VCEQ. So operating point or quiescent point, Q point, is the intended point of DC biasing without the AC input signal with the IB, IC and VCE set. So before we feed it with AC input signal, we will, like I said, and I'm repeating myself again and again, the BJT will have its biasing sorted out by the biasing circuit, and it will be set at the Q point. So what this plot shows effectively is the combination effect of the choice of BJT, the input loop and the output loop parameters. Okay, so what I mean is that the output characteristics, okay, the choice of BJT would give you the output characteristics, and this value of IBQ behavior in a plot which is IC versus VCE, which is the BJT in common emitter configuration, which is dependent on the value of beta. Okay, and the input loop would set IB, which of this IB would be, which of this IB level would be selected, and the output loop sets the load line. So this is a combination of all three: the input loop, the output loop, and the choice of BJT itself. And the intercept of all the information is the operating point or Q point. Okay, now let's have a look before looking further into what the load line tells us is how to avoid transistor insaturation. We know that for active operation, we know that the emitter-based junction should be forward biased, okay, causing resultant forward voltage VBE at approximately 0.7 volts, and that the collector-based junction should be reverse biased, which is VCB. But when we design the biasing circuit, we don't directly set VCB. Okay, what we set is VCE. So this means that as we set VCE with the value of RC, there is a value of VCE set that is too small that causes the collector-based junction, which should be reverse biased if in active mode, to be forward biased instead. So when both junctions are in forward bias, this would cause the transistor to go into saturation, which is not in the active mode of operation, and this would distort the amplifier. So for a given load line of an output loop, we know that the Q point is too close to VCE set if IC is approaching IC set. Okay, so I have just scribbled here onto the output characteristics for a given load line of an output loop. A given load line. Given load line means now you have already decided what RC is. Okay, and as you decide the different levels of IB, okay, this would correspond to the different levels of IC that you might want to decide for. But if you set IB too high, this would mean that your IC, okay, can be too high, which also means that the VCE Q point is also decreasing, and it may go less than VCE set. Okay, this implies that there is a maximum value of IC that is allowed for a given RC and VC parameters that have been chosen for the output loop. So the question is, what is the maximum value of IC for the chosen values of RC and VCC of the fixed bias configuration that you have decided? Okay, so an estimation of IC set of the Q point in the saturation region can be done by estimating VCE set as approximately equal to 0, because we know VCE set is going to be a small value. So this is actually slightly different from our earlier diagram, and you can see this in the textbook. And you can see that this shift here, we have assumed that VCE set is almost equals to 0, because what we want here is just a rule of thumb. Okay, it's not an actual figure, but we know that if it's too close to IC set, then it's not safe to design in that region. Okay, so in saturation condition, if we say that VCE set is approximately equals to 0, which means we're effectively saying that RCE resistance, internal resistance between collector emitter, is also estimated as 0 ohms. Okay, and this value here, IC set, can be found because if we do an KVL of the output loop of the approximate circuit with VCE estimated to be equals to 0 volts, it would give us IC set equals to VCC over RC. Okay, again, don't get confused. This is not the analysis of the output loop as such, but we are here trying to estimate what IC set is going to be. Okay, and when we want to estimate IC set, we estimate VCE to be about equals to 0, and IC set is about VCC over RC, which is going to be your y-intercept here. Y-intercept of the load line. So for a transistor operating in the saturation region, the current is a maximum value for the particular design. If we change the design, the value of RC, or maybe even architecture, the corresponding IC set may rise or drop. And this value of IC set here is a value that we want to avoid. Okay, so let's look at our previous fixed bias configuration example. We've done this. I'm just copy paste here. Okay, this circuit was given, and then we did this analysis earlier. Okay, from that analysis that we did of the input loop, we found that ICQ is, which is the question point, the Q point of IC is 2.35 milliamp. Now, just checking in case our value of RC was pushing this value right to the saturation value. So checking if the value of 2.35 milliamp exceeds the value of IC set to be avoided, i.e. checking if saturation operation is avoided. If I do IC set by estimating VCE to be equal to 0, VCE is not equal to 0 in this case, but we're just estimating because we want to know what IC set is. We find that IC set is 5.45 milliamp, so our design is 2.35 milliamp, so meaning this design is acceptable from the point of view of avoiding saturation. Also, in our previous example when we did this, remember we calculated VBC and we got it to be negative, and that shows that collector base is already reverse biased. So this is just like double proving it, okay? Double checking. So effect of RC, IB and VCC on load line and Q point. Now I'm leaving that topic of saturation. Let's have a look at how exactly RC, IB and VCC affects the load line. Okay, so the earlier slide says that the load line is linear line from the output loop superimposed in BJT with the y-intercept at VCC over RC and x-intercept at VCC. So this load line gives a graphical visualization of effect on BJT Q point of choosing values of RB, RC and VCC. So let's have a look at the first slide here. Okay, now let's look at what happens if you decide on a higher value of IB by setting different values of RB. So increasing values of IB shows that IC is also increased, which is what we understood earlier anyway. So IC is equals to beta IB, but there is a need to avoid the saturation value, so it's good to check. Now let's have a look at what happens if we change RC. We know that RC sets VCE. So increasing values of RC, okay, where R1 is smaller than R2 and R2 is smaller than R3. So as we increase values of RC from R1 to R3, we find that IC set also decreases. And also for the value of VCEQ, it is also changed accordingly. So for the same IBQ, because IB is not set by RC, IB is set by RB. For the same IBQ, increasing RC decreases VCEQ. Okay. So again, when you increase RC, there is that danger of approaching VCE set, which you would have to check in your design if you decide to increase RC. Also, what happens if you increase VCC? Now, increasing VCC has the effect of increasing VCEQ as well as IC set, okay, where you can see here that if VCC 3 is the smallest, you will find that the Q point is also decreased as the VCC is decreased. So whether you increase VCC or not, it does not cause significant changes on ICQ, because IC is dependent on IB and IC is equals to beta IB. So either you set a higher IB if you need a higher IC, or if you still have the freedom in your design to change the BJT, you may want to find a different BJT with a higher value of beta. So let's have an example on the fixed bias circuit load line analysis. So question, for a fixed bias configuration, given this load line, okay, in this case this is given, this load line is given, this output characteristics is also given, determine the required values of VCC, RC and RB. So this question already sets the architecture of the DC biasing circuit, which is the simplest DC biasing circuit, which is the fixed bias configuration. Okay, so I can draw an output loop, do a KVL, and this is what we get. Okay, so again, these are values that I don't have to remember because it's dependent on the circuit architecture. I can just do a simple analysis of KVL, and I find that the y-intercept is VCC over RC and the x-intercept is VCC. So 10 is VCC over RC and 20 is VCC. Okay, so the solution is, so VCC is 20 volts at IC equals to 0 milliamp, and IC is VCC over RC, which is given to be 10 milliamps. So I find that RC is equals to 2 kilo ohm, IB is estimated from the graph itself because it was between 20 and 30 microamp. So we choose IB to be about 25 microamp, and we find that RB is 772 kilo ohm, and we see the difference in values of RB and RC. Okay, so what this example is trying to point out is that from this example we can see that if we know the DC biasing circuit architecture and we know where the Q point is intended, we can design the network resistive values that will bias the transistor at the desired Q point. Okay, we're done with the fixed bias configuration. Do attempt the tutorials that your lecturers would have given you over the Google Classroom sessions. In the next video lecture, we will cover video 3, video pack 3, which will still be on DC biasing circuit, but it will be a continuation for other DC biasing circuit, not fixed bias configurations, with common emitter being the majority of it. Thank you. See you next video. Assalamualaikum.